Welcome to The Explainer. I am absolutely thrilled to have you here today because we're about to unravel what is, literally, the greatest detective story in the cosmos. We're looking at some absolutely groundbreaking advancements in high-resolution radio astronomy and theoretical cosmology that are, quite frankly, completely reshaping our understanding of the universe. So, buckle up, because we're going to explore how the very fabric of space itself might actually be carrying the answers we've been searching for all along.
Okay, let's dive right into this. For decades, we've stared up at a universe packed with billions of galaxies, each bursting with billions of stars. And we keep asking one really simple question. Where is everybody? You know, the infamous Fermi paradox. Mathematically speaking, the cosmos should be absolutely teeming with advanced civilizations. Yet, our radio telescopes, they hear nothing but the random static of dead stars and cosmic dust. But what if the entire premise of our search is just wrong? What if our failure to find signals isn't because no one's out there sending them, but because we fundamentally misunderstand the medium itself? Think about it. What if they're screaming into the void, but we're basically listening with the wrong kind of ears?
To wrap our heads around why we might be missing the message, we have to look at the difference between standard linear broadcasting and topological transmission. Honestly, it's kind of like humanity is out there trying to explore the cosmos with a rotary phone, while the rest of the universe is already streaming in interdimensional fiber optics. See, standard linear broadcasting relies entirely on tweaking the amplitude or the frequency of a signal to embed data. It's linear, it's pretty straightforward, and it's exactly how we humans communicate. But topological transmission? That uses what are known as off-axis polarization gradients inside a high-gain manifold resonator. So instead of just changing how loud or fast a wave oscillates, this method literally encodes data directly into the three-dimensional geometry of the wave itself. It's the difference between listening to a single note get louder and softer versus trying to read a dynamic, twisting 3D puzzle hurtling through space.
Section 1. Mapping with radio bursts, probing the cosmos.
Right, so before we can even begin to decode these twisting 3D puzzles, we really need to understand our current tools. Enter fast radio bursts, or FRBs. These have evolved from just weird cosmic anomalies into our absolute premier cosmological probes. Astrophysicists use a tool called the dispersion measure, or DM. When these super-fast, high-frequency radio pulses, like FRBs, travel across massive cosmological distances, they don't just zip through an empty void. They actually crash through the intergalactic cosmic web, interacting with free electrons along the way. And these electrons cause a frequency-dependent time delay on the burst. By carefully measuring this exact delay, modern observatories can calculate the column electron density. This lets us map the diffuse baryonic matter, the normal physical stuff, hiding in the dark, unmapped spaces between galaxies with a precision we've never had before. It's essentially like shining a flashlight from a billion light-years away just to map the fog it cuts through.
And building right on top of that, we have Faraday rotation measures, or RM. If the dispersion measure maps the physical stuff, RM is our incredibly sensitive probe for magnetized plasma environments. When a radio burst punches through a host galaxy, we detect these sudden, reversible fluctuations in the RM. Think of these fluctuations as a cosmic fingerprint. They reveal incredibly complex magnetic boundary layers, intense companion star interactions, or these super-dense plasma structures. By reading these measures, astrophysicists are literally decoding the chaotic, intense environments right where these massive bursts are born. We're learning to trace the physical and magnetic journey of a signal well before we even try to decipher its message.
Section 2. The VORTX Cosmological Framework, Personal Harmonic Cosmology.
Now, to truly grasp all of this, we need to step away from traditional linear astrophysics for a minute. We're moving into a revolutionary framework developed by Mr. Hardin, which gives us the theoretical backbone for how complex geometry actually governs the cosmos. This is the 5-formula engine, the beating heart of the VORTX model. Check out these interconnected concepts. First, the toroidal path identity, showing us that paths are closed and transcendental. Then, the Fibonacci scaling factor, proving that expansion is nonlinear and self-similar across different scales. Next up is the Planck scale harmonic constant, which suggests that layers of reality are hooked together by vibration, not just adjacency. We've also got the divergent yaw equation to account for observer measurement drift, and finally, synthropic equilibrium, meaning the whole system naturally self-balances to maintain absolute order. What's so wild about this framework is that it seamlessly weaves together math, physics, astrophysics, and engineering into one recursive toroidal structure, and it explains these mind-bending cosmic phenomena without needing to invent any exotic, unproven dark components. It's a total game changer.
Which brings us to a really profound realization known as Hardin's loop. Quote, any attempt to impose a static, linear definition on a recursive toroidal manifold inevitably collapses. Let that sink in for a second. In this model, our failure to find simple, straight-line answers in the universe isn't because our telescopes are broken. It is functional proof of the universe's dynamic architecture. It proves that space is frequency-based, phase-dependent, and deeply tied to the observer. The universe simply doesn't do straight, static lines. It does recursive, looping geometries. And if the universe communicates in geometries, well, wouldn't any intelligence that mastered it do the exact same thing?
Section 3. Linear versus topological broadcasting, rethinking the signal.
Okay, so we've mapped the cosmos and we've established this toroidal geometric framework. So the crucial point is this. If you are a highly advanced civilization living in a toroidal universe, you're absolutely not going to just shout linearly into the void by cranking up your raw power. You aren't going to pump more energy into an AM/FM broadcast and just pray someone hears your static. Instead, you'd use structural encoding. You'd use a high-gain manifold resonator to modulate the actual spatial and angular distribution of the polarization vector right across the expanding wavefront. You don't make the signal louder, you meticulously engineer the physical geometry of the signal itself as it ripples through space. You embed your data right into those off-axis polarization gradients. You're basically turning the wave into a readable 3D topological blueprint.
Section 4. Encoding via polarization gradients, manifold vector rotation.
Now, this is where the suspense really builds, because we're not just talking theory anymore. The source material outlines the exact sequence for how a signal gets topologically twisted, a process called manifold vector rotation. And this brilliantly illustrates how it works in 3 steps. Step 1. As the signal is born, it goes through phase cavitation in the F-band and R-band tension. Because of this, the resulting wavefront, whether it's electromagnetic or neutrino-coupled, doesn't oscillate smoothly. Step 2. The sender introduces ridiculously precise microperturbations to the local magnetic field lines, maybe using something as massive as a magnetar cavity. And finally, step 3. These tiny perturbations force a dynamic twisting of the polarization angle off-axis from the main propagation path. By forcing the wave to twist at highly specific, engineered angles, you can embed a virtually infinite amount of complex data right into the gradient of the wave. The crazy part? To one of our standard linear antennas, this masterpiece of engineering just looks like a random, chaotic burst of dead energy.
Section 5. A Fermi paradox solution, the cosmic revelation.
So we've traced the whole path, right? From mapping galactic plasma with fast radio bursts, all the way down to the tiny microperturbations twisting a signal's polarization gradients. And when you connect this massive macro scale to that intricate micro scale, the greatest mystery of our time suddenly clicks into place. We were listening for volume, but they were transmitting in geometry. I mean, that is the ultimate punchline to the Fermi paradox. For over 50 years, humanity has aimed these massive dish antennas at the sky, waiting for a simple, linear beacon, a blip on a screen like a traditional radio station. But if truly advanced intelligences are speaking across the cosmos, they moved past AM and FM a long, long time ago. They're leveraging the toroidal physics of the universe itself. They are speaking in topological twists, hidden right there in the off-axis polarization gradients of massive high-energy events like FRBs. The universe isn't silent at all. Actually, scratch that. It might be deafeningly loud with information, encoded directly into the shape of the very light crashing into our telescopes. So I want to leave you with this final, provocative thought. Are we finally ready to tune our instruments to the geometry of the universe? Our technology is just now reaching the point where we can actually map these intricate, recursive toroidal topologies. We can measure the dispersion, and we can trace these manifold vector rotations. The next step isn't about building bigger antennas to just listen harder. It's about upgrading our models to translate the spatial shapes of the signals that are already hitting us. Thank you so much for joining me on this explainer today. I really hope it leaves you as pumped as I am to see what we'll discover next when we finally learn how to truly listen.